Hello everyone, in this video I wanted to share with you a script that estimates the Hurst exponent using Python. So for the background, we know that the exponent, if it's less than 0.5, it's considered as anti-persistent mean reverting, where like a sharp upward movement is followed by a negative movement, so it's jagged. If it's 0.5, the process is memoryless, or it's a standard Brownian motion. If it's higher than 0.5, it's considered persistent, or we can see a trend. So, for the estimation methods, the first thing we did is the rescaled range RS analysis. It's in here, I believe, yes. So basically in this function, what we did, the time series is divided into non-overlapping contiguous chunks of size W, and then for each chunk we calculate the mean adjusted series. So yt is xt minus the mu, and then we compute the cumulative deviation. Then the range R is defined as the difference between the max and the mean of the cumulative deviation using max and mean. So and then the standard deviation we computed of the chunk, and then the rescaled range is R over S. So this is averaged over all the chunks of size W, as we said. This process is repeated for various window sizes logarithmically spaced between a minimum and a maximum. And finally, we fit the linear regression of the log-log plot window size W against the expected RS value. The slope of this line is the Hurst exponent. And next we have the variogram estimator. So for a given time lag, we compute the expected value from the squared difference. So xt plus the time lag minus xt squared. For similar processes like the fractional Brownian motion, the variogram scales as the variance, like the time lag to the power of 2h, and then we compute the v lag for multiple lags, and then we regress with the log against log of the lag, and then the slope of the regression line equals to h. So the Hurst exponent is estimated as slope over 2. And then we will simulate the fractional Brownian motion using this function. So the first step is we generate the autocovariance, and then we build the Toeplitz covariance matrix. And then with the Kolsky decomposition, we find the lower triangular matrix, and then we generate standard normal variables z and multiply L by z to obtain a sample path of the fractional Gaussian noise. And lastly, we compute the cumulative sum of this Gaussian noise to yield the fractional Brownian motion path. So for the plot, we get this one here. As you can see, we're using both methods and the ideal. So if the known target values are 005, 01, 02, all the way to 09, it evaluates both estimators and outputs the comparison to the terminal. So this plot visualizes the true Hurst exponent on the x-axis against the estimated Hurst exponents on the y-axis, with a 45-degree reference line representing the ideal estimator.